Okay, welcome to the seminar. This is our third seminar here every week on Thursday. We have a good talk today, I believe, and I wanted to remind people how the seminar speakers were going. Maybe some of you didn't know you were up speaking soon. I'm checking my list here. You can see me afterwards. Kazi, you are next week, so you can blame Professor Al-Qadi for not telling you. Tor would be in 2 weeks. Then we'll have a visiting scholar under Professor Tutumler's group, and then Hassan would be right before spring break. Yeah, Hassan Kazmi. Today we'll have a talk from 1J, and he'll be talking about mechanistic empirical evaluation of aggregate base and subbase qualities for flexible pavement performance. And he's been a student here since 2008. He's taken some of my courses and probably everybody's courses here. He's from Tongji with a bachelor's, master's from Southeast China, and he's hoping to finish his PhD soon, I assume.
Yeah.
Okay, so let's welcome him.
Okay. Thanks for the nice introduction. Just to make sure, can people sitting in the back can hear me? Okay. Yes. So. Good afternoon, everyone. Thanks for being here. Today, I'm going to talk about some results about the research project I have been working on. So the title is Mechanistic Empirical Evaluation of Aggregate-based Granular Subbase Quality Affecting Flexible Pavement Performance. Some of the work in this presentation was completed maybe 1 year ago, so some of them are still ongoing. So before I move on, I would like to acknowledge Minnesota Department of Transportation for providing the research funding and provides us the database. And I would also like to thank Professor Tutumler, Mr. John Sigma, Mr. Yu Chen for their contributions as well. So here's the outline of my presentation. First of all, I will give you a brief introduction about this project, and then I will start talking about the important aggregate qualities, and then I will present some results about how the aggregate quality affect pavement performance from the mechanistic pavement design perspective. At the end, I will try to mention some implementation work we are currently working on, as well as some conclusions and following up research. So, as in Minnesota and in many other places, unbound aggregate materials are becoming expensive and scarce, especially for high quality clustered ones. So under such circumstances, maximize the use of locally available marginal quality aggregate sources become a major concern for state DOTs in terms of promoting sustainability and achieve cost effectiveness. But if we look at current material specifications, they may not encourage the use of those lower quality materials. So here in this project, we are trying to identify if we can optimize the use of those lower quality materials. Here is just two typical examples from Minnesota. The first one was found by Lukeland in 1980 when he applied actual road test results to design flexible pavements in Minnesota. What he found is certain MnDOT class 3 aggregates, which is lower quality, were even stronger than class 6 aggregates, which is a little bit higher quality. Similar, this interesting finding was also confirmed in mean road FWD field testing evaluation. For both thin and thick asphalt pavement, sometimes class 3 materials can have higher back calculated modulus than the other classes. So from those two examples, we may realize that there's a potential for those lower quality materials to be used for achieving cost effectiveness. So just to give you idea about those different aggregate classes, for aggregate-based materials, we have they have 5, 6, 7. They are basically clustered materials. And also shown in this table is some default design modulus currently included in MnPay flexible payment design program. And this table shows the granular sub-based material classifications. Class 3 and Class 4 are two major types. They are basically unclassed gravels. Here's the gradation binds for those different aggregate specifications. So the major objective of this research is to demonstrate that when we implement mechanistic payment analysis, can we achieve some economic benefits for using those locally available aggregate sources to minimize purchasing some high quality crossed materials. And the next objective is to develop some a new granular material selection software module to be added into the MnPay program to facilitate their payment design. The ultimate goal is to promote more economical use of those lower quality, locally available materials in Minnesota. So under those objectives, the following major tasks have been conducted. The first one is to establish linkage between important aggregate properties and mechanistic design inputs, such as modulus and strength. The second one is to conduct sensitivity analysis to identify how those mechanistic design inputs to payment life expectancies. Then we try to recommend some guidelines for developing performance-based material specifications. As I mentioned before, in terms of implementing the research findings, we are trying to develop this new granular material selection tool component for MnPay program. So in terms of aggregate quality, it's a very broad concept. It can mean a lot of things. But in this study, we refer quality exclusively to structural support, which means stiffness, resilient behavior, shear strength, permanent deformation behavior, not to other important ones like durability, friction, and so on and so forth. As you may all know, the first three are very important properties for unbound materials. And the fourth one, moisture suction relationship, is also very important because most of the time, granular materials and subgrade soils, they are not fully saturated. Actually, they are partially saturated. So this makes the suction an important factor to consider. We have collected a very comprehensive resilient modulus database from MnDOT. In this database, in addition to gradation information, we also have some results from the laboratory track cell testing for resilient modulus and shear strength. Note that those resilient modulus samples were collected from different construction sites in Minnesota. So it covers a wide range of different types of aggregates. This table summarizes the different aggregate types, and we can see that different gradations are included. Different aggregate classes are included. We have standard and recycled materials. This figure is a typical result of this database. The left figure is for aggregate-based materials. The right one is granular sub-based materials. Both of them are at optimal conditions. So one interesting observation I want to talk about right now is, as you can see, based on depending on the resilient modulus and the shear strength calculated by the peak deviated stress at the failure, we can classify those materials into a better quality and a lower quality. As you can see, the aggregate types falling into the better quality category are mainly some high quality crushed ones like limestone, crushed limestone. But you can also see like in this better quality category, some gravel materials are also falling within this category. So that means if we classify those materials based on traditional specifications, that may exclude the use of those materials. So that justifies the objective of this research study. So the important thing we can take from this figure is that when we evaluate the performance or quality of aggregate materials, we need to examine those three important factors, important behaviors simultaneously, not to just look at one of them. As you can see, we analyzed different aggregate properties ranging from gradation to shape properties. Those factors are interacting with each other to affect the resilient modulus and shear strength behaviors. So as I mentioned before, the first major task is to develop some empirical correlations between aggregate properties and mechanistic design inputs. This way, pavement design can estimate those important mechanistic properties without running some time-consuming lab testing. So to this end, we did some multiple linear regulation analysis, and the one important thing we noticed that in the past years we have found aggregate shape properties play a very important role in those behaviors. So we requested 12 samples from MnDOT for imaging analysis, and then we incorporate those results into the regulation analysis. Here is just a summary of the aggregate shape indices we analyzed. This is the correlations we came up with. I want to mention that actually before the incorporation of aggregate shape properties, those correlations were not that good. But once we incorporate those correlations, incorporate those aggregate properties, the correlations were improved. So right now we are trying to further improve and validate these correlations using both MnDOT databases and our own databases. So in the last 2 years, we have been analyzing a lot of aggregate samples from Tensor for image analysis. So we are trying to further improve this using this database. As I mentioned to you before, right now in MinPay program, there are some default resilient modulus for different aggregate classes. So because we already have this empirical correlation, we try to validate the reliability of those default design moduli using Monte Carlo simulation. Basically, it's a very simple concept. Once you have a model, let's say fx, then if you know the individual distribution for each input, then you can estimate the distribution of the output. From this MnDOT database, we were able to obtain the distribution for each input parameter. Because we have two stress terms in that resilient modulus constitutive model. So we calculate the representative stress levels in base layer and sub-base layer using MinPay program. This table shows the typical pavement structure used in Minnesota. And also shown are the representative stress levels calculated. So without, instead of elaborating the details, here just shows the final results. We can see that currently the default moduli for aggregate-based 24 KSI, the reliability is larger than 95%. And the granular Subbase 11.7 KSI default moduli has a reliability of 87%. So that means those default moduli is kind of reasonable if you don't have exact information. Another information we got from the Monte Carlo simulation is the sensitivities of each individual parameter to resilient modulus. As you can see, the dry density turns out to be the most positive one, and the FE ratio, angularity, and the surface texture shape properties, they also have some kind of significant effect. This is for stress level in aggregate base. Excuse me. Yeah. Okay, sorry about this. Yeah. And this is for the stress level in Subbase. You can see pretty much similar trends for density and as well as the shape properties. And we also did some form analysis to confirm the trends we found from the Monte Carlo simulation. Basically, it's we can also identify the order of importance of aggregate source properties. Because since I don't have enough time to talk about the details, so I just show the final results. The left side shows the results from Monte Carlo simulation, which we just looked at, and the right-hand side shows the form analysis results. As you can see, both methods were able to identify similar results. So the most important factors are listed in the bottom. We can see density and gradation and moisture and shape properties. They are kind of the most significant ones. As I mentioned before, in this database, we have different gradations. So another study we have done is to identify the gradation effects on the mechanical behavior. Actually, this is this includes a lot of materials, so which I don't have enough time to talk about today. So I just summarized the most important findings from this study. We found that probably we can further redefine some optimal zones in the current gradation bind. For example, right now we identified the GS ratio calculated from the formula list in the bottom right. It tends to have an optimum value between 1.5 and 2 to achieve the better shear strength performance. And these findings has also been confirmed from some external aggregate databases, like, for example, Professor Thompson's database in 1997, and our own database from 2009.
What is G2S ratio?
The gravel to sand ratio, which can be calculated from the formula I listed at the bottom. So,
Gravel over sand ratio?
yes. And another thing we are trying to study is how the gradation will affect the moisture suction relationship. For example, we can find if there is any relationship between the soil water characteristic curve parameters and those gradation parameters. This is about another task for a different project we are working on right now. The goal is to come up with some redefined material class specifications. For example, instead of have class 5 and 6, we can further classify them into, for example, class 5A, 5B, 5C, based on the gradation and the aggregate shape properties. The one thing we are trying to explore is that if we can use the discrete element modeling based simulation for this purpose, we are trying to simulate the triaxial testing and also the shear box testing. Although we need to make some compromise for gradation, we cannot cover some very fine gradations because of the computational efficiency. But the ultimate goal of this project, this one, we just to study limited gradation and with a wide range of shape properties to see how those two factors can be optimized to come up with redefined material specifications. Right now we are working on this one for another project. So after that, I will talk about some mechanistic empirical payment evaluation results about aggregate quality. So we to select different quality levels, we select three different quality levels for base and sub-base materials identified as high quality, medium, low quality. Here is the gradation and of those samples, representative samples we selected from this database. This slide shows how we selected those representative quality levels. First of all, based on the first thing we look at is the resilient modulus. So the high quality has the highest resilient modulus, and also the lowest one has the lowest modulus. Another thing we also look at is the shear strength behavior. As I mentioned before, we need to examine both shear strength and the resilient modulus pavement deformation behavior simultaneously to evaluate the quality. So another thing we double check is if higher resilient modulus also had the higher shear strength. So we examined those two factors together and came up with representative quality levels. And this is for sub-base materials. So with these three different quality levels, we were able to run some GT-based analysis, because for the mean pave analysis, we need to input a single resilient modulus. So what we did is to get a equivalent resilient modulus value from the nonlinear modulus distribution, and then input into the mean pave program. This is just a summary of the equivalent modulus values for different pavement structures. Sometimes the granular sub-base materials have a slightly higher modulus than the aggregate-based materials. And then we came up with a sensitivity analysis matrix. we have different pavement structures. We have two climatic regions. Also, we have different thickness combinations. So another objective of this sensitivity analysis matrix, which we can come up with a design category for designing low volume loads. This way, because if we know the soil subgrade condition, we know the traffic, we know the climatic region, then we can just use those results without doing any further analysis. These some typical examples in terms of fatigue cracking. As you can see, the horizontal axis represents the base layer thickness. The vertical one represents the fatigue life. So if we increase the quality, then we can have a longer fatigue life. That's as expected. So, but another thing we can see that if we have a very low quality base material, increasing thickness, it doesn't seem to help that much. So,
can you define HH and
LL? Oh, from now on, when I say HHLL, I mean the first letter represents the quality of base materials, and the second one represents the quality of the sub-base material quality. This figure shows the aggregate quality on fatigue life. As you can see, the horizontal one represents the pavement service life. The vertical one represents percentage of pavement sections meeting pavement service life requirements. As you can see, there's some significant difference between different quality combinations. And the HH combination, if we use if we use high quality material in both base and sub base, then we can have much better performance. That as our follows our expectation. For high and low quality combination for sub-base, another thing for rutting performance, if high quality sub-base materials are used, then the quality of base material seems to have some trivial effect on the rutting performance. So that means for design low volume loads, if we have a weak subgrade, then we may consider using some high quality sub-base materials.
So LH is better than HL?
Yes, in terms of the rutting performance.
The arrows have moved, I guess, but you're trying to make the point that a high quality subbase is more important than a high quality base, in this case for rutting. Mm-hmm. Whereas the trend was opposite, because base is providing support for asphalt, correct?
Yes.
Yeah, okay. What's the criteria for rutting? I didn't quite get that.
The criteria for rutting is based on some transfer functions based on the compressive vertical strength on top of subgrade, and
so the rutting criteria is only in the subgrade.
Yes.
Okay, so you haven't considered actually the subbase may actually rut.
Yes, that's another thing I'm going to talk about later. So right now we just use mean pave analysis. So fatigue is based on the tensile strength at the bottom HMA, and rutting is based on the vertical strength and on top of subgrade.
Well, just like I guess Asphalt Institute, mean pave only considers rutting coming from subgrade.
And this shows the case for when we have high volume traffic. So that means when the traffic is very high, so probably those low quality materials may not be that cost effective in terms of both fatigue and rotting. This figure shows the base thickness effect. As I mentioned before, if we increase the base thickness, that can improve some rotting performance. But however, fatigue performance doesn't seem to benefit a lot from the base thickness increases. This slide shows the subbase thickness on fatigue cracking and rotting performance. Increased subbase thickness seems to slightly improve rotting and fatigue performance. But as compared to fatigue performance, rotting performance can benefit much more from the subbase thickness increases. This part is just, we first of all, we select 3 different quality levels for aggregate-based and sub-based materials, and then use GTPave to get one equivalent resilient modulus for input into MnPave program. Then we got some pavement performance from mechanistic pavement design perspective. And in that analysis, we didn't consider some important factors. For example, we didn't consider the base rotting, sub-base rotting. We only consider subgrade rotting. And the second thing, we use some linear elastic analysis. So this part, I will supplement the previous findings by doing additional study on this topic. So I used GTPave nonlinear finite element program. This is the finite element model for this pavement structure. So in terms of loading, we have 9 kip single wheel load and 100 psi pressure, uniform pressure. And we didn't analyze all of the pavement structures, but we just add a portion of the pavement structure to validate the previous findings. So in this case, with the capability of GTPave, we modeled the base and sub-base layer as stress-dependent, close anisotropic. The subgrade was using a bilinear model. And we just did one single seating analysis, just 4 seatings. So basically, the module is just for the 4 seatings, so standard 4 seatings. We didn't do a full seating analysis as we did previously for MnPave program. Because in their database, they didn't run some resilient modulus testing for close anisotropy. So what we did is we used some methods proposed by Professor Tumler and Thompson to estimate the close anisotropic model parameters. Here is the procedure. And here is the model parameters we estimated for different quality levels. So in this case, instead of having 3 different quality levels, we just had 2 quality levels, high and low, for base and sub-base. Another thing, as I mentioned, because in the previous analysis we didn't consider the rotting in both base and sub-base layers. So in this case, we are trying to take this into account. But right now, because there's no well-calibrated rotting prediction model for those materials, so a compromise we did is to evaluating the rotting potential from some more column-based failure criteria. And because we need to use some strength parameters for base and sub-base materials, so we use some default strength parameters in MnPave as minimum requirement. For example, when we say high-quality materials for base, the default strength parameters for forces, and we use as the minimum requirement for high quality base. And the spring strength parameters were used as the worst case to represent the low quality materials. Here are the two stress ratios we can calculate based on the Moore-Coulomb failure criteria. The bottom left one was proposed by Professor Tutumla and his student for limiting the permanent deformation or rotting of the unbound granular material layers. So basically, this shear stress ratio is the applied shear stress over the shear strength, and the upper right one shows the PQ diagram, which is kind of effective in evaluating the rotting potential of unbound layers. So as you can see, based on the shear strength parameters I just reviewed, so we can come up with these four different lines to represent low quality, high quality base and subbase materials. So for any stress points below these lines, we can say that it may not have very serious rotting, but any stress stays above this line, then we need to consider the rotting failure. These four figures shows the effect of aggregate quality on fatigue cracking in terms of tensile strength at the bottom of HMA. As you can see, high quality base materials significantly reduce the fatigue cracking. The up two figures, you can see the equality line. Those points are scattered below the equality line, which means high quality base have much lower tensile strength than the low quality base. But for the Subbase case, those points were scattered around this, pretty much around the equality line. So the effect is not that obvious. This is another figure for fatigue cracking. The vertical axis is the allowed repetition for fatigue. As you can see, the low quality base, high quality subbase, and low quality base and low quality subbase, they have pretty much similar allowed repetition for fatigue. And if we have a higher quality base, then we can have much larger allowed repetition for fatigue. That was found from the previous mean pave analysis. So this GT-pave analysis also confirms the important role of base quality in controlling fatigue cracking. Another thing we didn't consider in the previous mean pave analysis is we didn't consider the initial construction cost for different qualities. Because if we want to use higher quality materials, probably we need to haul them from a longer distance. If we use some local aggregate sources, we may save some construction cost. So we did a very simple initial construction cost analysis. So, but because we focus on the quality of base and subbase layers, so we didn't consider asphalt and subgrade related costs. And this table shows some typical parameters we used in this cost analysis. As you can see, when the subbase thickness is larger than base thickness, if we use high quality base, low quality subbase, that will reduce the initial construction cost. This way, it can be more cost effective in terms of fatigue cracking and initial construction costs. And this slide shows the rotting potential evaluation results. those two figures represent two stress ratios calculated from two different methods I just mentioned. The first one is the shear stress ratio, and the bottom one is the stress ratio calculated from the PQ diagram. The left vertical axis represents the base stress ratio, and the right vertical axis represents sub-base stress ratio. The points here represent the maximum stress ratio within each layer. It's kind of a busy plot, but we can still make some observations from them. So if we look at the ALH combination, which is low quality base and high quality sub-base, we can have much lower sub-base stress ratio, and the base stress ratio doesn't increase that much. And this slide shows the subgrade rutting potential. In terms of subgrade rutting, we use the subgrade stress ratio proposed by Professor Thompson. Basically, it's deviated stress over unconfined compressive strength. So we can see like ALH combination results in a lower deviated stress and thus a lower QU requirement for subgrade. This figure shows the layer thickness results on fatigue cracking. This actually is pretty much similar as what we found from previous mean pave analysis. For example, if we have weak base materials, increasing the base thickness doesn't seem to be a very effective approach. Sub-base thickness, if we increase sub-base thickness, it can improve fatigue cracking performance, but not that significantly. I will briefly talk about some implementation plan based on our findings. So these are the different components. The first one is for aggregate source selection, because they already have an online database for all the aggregate quarry and pit locations. So if we incorporate that database, then we can come up with this component. The other one is to estimate the design property using the developed correlations I just mentioned. Another component is we can do some cost-effective analysis to make decisions between which kind of aggregate sources we can use based on the performance and the cost analysis. So I already talked about this because similar to the idea like soil class, right now they have function, you can easily locate the soil class for any single location. And similarly, we can also develop this interface. This way we can easily know what kind of aggregate sources we can use if around any construction site. This interface is to estimate some important design properties for intermediate or basic level design purposes. This one is to optimize the utilization of aggregate source locations based on the performance and life cycle cost analysis. Just a quick summary of what we found. We first developed some correlations for intermediate and basic design purposes. So we found that aggregate shape properties is a very important thing to take into account. And then through some mechanistic pavement analysis, we found that for low to medium volume roads, those lower quality materials can be optimized in pavement construction to achieve cost effectiveness. Another thing I just briefly mentioned but didn't talk in details is we can do some more work on the gradation and the shape combination to optimize the performance. Because in terms of lower quality materials, what we can do is to optimize gradation shape properties to try to achieve as higher performance as possible. And the other thing I briefly mentioned is about the granular material selection tool components we propose and currently working on. Following up research, we know that those analyses are based on 2D analysis, so it cannot be very accurate. So what we are trying to do is right now we are trying to do some 3D finite element simulation. We couldn't do that before because we have a comprehensive matrix, so we don't have enough time to run all the 3D analysis. Another thing we are trying to consider is we can model the granular materials as elastoplastic. And in terms of permanent deformation, all the previous research are based on the small deformation theory. So another thing we can try to do is we can analyze permanent deformation using elastoplastic constitutive model within the finite deformation framework. So another possible way for us to explore is how can we incorporate the unsaturated soil mechanics into the finite element analysis. So right now, those three directions are the ongoing research directions. So with that, I thank you all for your attention and welcome any comments, questions.
We have a couple minutes for questions, comments from the audience. You spoke about in the beginning about the matrix suction and how important that was, but I don't remember seeing anything about it.
Yes, this thing was not included in the scope of this study, but because the type chair, John Sigmar, he has been working on this area for several years. So that's kind of the idea he proposed to us to take into account. So in the following up researches, so.
It's in MnPave actually, but if you go with fall only, other than the 5 seasons, they have.
Yes, right now in MnPave program, they did include some of the unsaturated mechanics results into the MnPave analysis. For example, the first slides I show some default design moduli. So those are based on the seasonal resistance factors from unsaturated soil mechanics analysis.
Right, MnPave has 5 seasons actually for analysis, and because Minnesota is up in north, so obviously that's a main consideration. The spring thaw is a big thing over there, and load restrictions and things. So what they do is they have a second spring season where they have all the thawing going on in May, late May even. And right at that time, this is their worst season to take into account those effects and the lowest modulus properties and strength properties. And that. In our study, we were more focused on, I guess, the lab data and relating to aggregate properties and going through the sensitivity analyses to look at what quality material would be better used in what location in the subbase or base from rutting or fatigue cracking perspectives. So we were just given the task to use only the full default design modulus at this time. That's why he's bringing at the end in his talk here. Obviously, the seasonal effects will have to be factored into all of the quality aspects. So, yeah.
Okay, any last questions? Okay. Juan J., thank you. We'll see everyone next week, same time.